Hey everybody, how you doing today? We're gonna do our last section that we're gonna do in chapter 11 here. It's called the Binomial Theorem. This is 11.4. This is college algebra at College of the Sequoias in the fall of 2020. And so what we're looking at here is called the Binomial Theorem. And some of these things will look familiar to you, but some of them, we're gonna build on that. I'm going to start down here. If we have x plus y squared, remember that's just x plus y times x plus y. That's what we're building off of, doing stuff like that. We have, and I'm deliberately writing in the 1 for a reason, you'll see, 1x squared plus 2xy plus 1y squared. If I go backwards and I lower it by a power, lower it down to 1, it's just 1x plus 1y. Again, the 1s are there for a reason. And x plus y to the 0 power is just 1. If I want to go further, I got x plus y cubed. I'm going to multiply this by x plus y. And what we get is x cubed plus, once you clean it all up, plus 3x squared y plus 3x y squared plus y cubed. And I'm going to throw 1s in front here just so you can see it better. X plus y to the 4th. 1x to the 4th. We've got 4x cubed y plus 6x squared y squared plus 4xy cubed plus 1y to the 4th. And why not? Let's go down to y to the x plus y to the 5th power. We've got 1x to the 5th. Then we've got 5x to the 4th y. And then there's a 10x cubed y squared, a 10x squared y cubed, a 5x y to the 5th, and a y to the 5th. Now, what I've had here, if I call this n, what I'm looking at is, is there a shortcut for x plus y to the n? Is there a shortcut? Let me rewrite that x plus y to the 5th out again so I can add a little space to it. And I'm going to deliberately add in the exponents when they're missing, when it's a 0. I will 5th right there. That's a 4th. And I missed my 1 right there. Got a little hasty. And I'm going to throw a 1 here on these ones, just so it makes it a little bit clearer. Couple things to note. The exponents add up to n. Five plus 0 is 5. 4 plus 1 is 5. 3 plus 2 is 5. Like that. The exponents follow a pattern. We start off with x to the n, y to the 0, and we end up with x to the 0, y to the n. And as we go this way, each step we do, x goes down by 1, and y goes up by 1. So 5, 4, 3, 2, 1, 0 on the x's, and the y's go 0, 1, 2, 3, 4, 5. The question is there an easy way? That part's easy to remember. You're just counting numbers, 0, 1, 2, 3, 4, 5, or counting down 5, 4, 3, 2, 1, 0. The question is there an easy way to remember these coefficients out in front? And it turns out there is. Is there an easy way to remember the coefficients? Yes. And it is called Pascal's triangle. I'll show you that right now. So this is called Pascal's triangle. And I'm going to list my ends here for a little while. And why not? We can do one more. So you start off the top of the pyramid has a 1. And the next row down is 1 and 1. And as you keep going down, you keep putting 1s on the outside. And you add up the two numbers above it. 1 plus 1 equals 2. And then I'll go again. So that's n equals 0 line, n equals 1 line, n equals 2 line, n equals 3 line. We're going to have 1s on the outside. I will add up the numbers above it. 1 plus 2 is 3. 2 plus 1 is 3. I go to n equals 4. 1's on the outside. Do all these. Add up 1 and 3, I get 4. 3 and 3, I get 6. 3 and 1, I get 4. If I do the next line, 1 plus 4 is 5. I wanted that in blue. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. Notice these are all the coefficients we had right here. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1 is n equals 4, or n equals, yeah, 4. N equals 5, 1, 5, 10, 10, 5, 1. We do n equals 6. I've got 6, 15, 20, 15, 6. So, knowing that, I can do x plus y to the 6th pretty easy. I start off with x is capped at the biggest exponent of n. So I'm going to have x to the 6th, y to the 0, which I won't write. And there's one of them. And then I'm going to have 6 of the next one. X goes down by 1 and y goes up by 1. And then the next exponent or coefficient is 15. X goes down by 1, y goes up by 1. And we keep following the pattern. X goes down by 1, y goes up by 1. And it follows this nice little simple, easy pattern. Now, you don't want to have to do this triangle for x plus, like if you really, really wanted a big one, like x plus y to the 13th, I don't want to draw the whole pyramid up to 13. That's a pain in the butt. There's another way to do these coefficients. Let that sink in for a second. So this is what this is the binomial theorem. These are called the binomial coefficients. And where is there a shortcut for them? There is. The binomial coefficients if we have integers n and r, where r is less than or equal to n, the binomial coefficient is called this. They say NCR, and the reason why I'm showing you that way is because this shows up on a calculator and makes it really quick. Another way to write that is like this. I use uppercase R there. I'm going to use uppercase R here. They tend to use lowercase r, but that works just as well. And choose r is this formula right here. N factorial over, r factorial, n minus r factorial. Okay. And this is read as n choose r. They often write it like this. I'm not sure why. This is just as clear. This is a calculator button. But just so you know, factorial, this is that right there, we say is n factorial. And factorial factors are outcomes of or things in multiplication, right? That's an indicator of what that means. N factorial is n times n minus 1 times n minus 2 times ... times 3 times 2 times 1. So you just keep subtracting a number and multiplying it by the previous number until you get down to 1. This works all the way this is for n is greater than or equal to 1. When n equals 0, 0 factorial is defined to equal 1. And the reason for that is, notice if we have this here, we do not want 0 factorial to go down to 0. That would put a 0 in the denominator. That would be bad juju. We don't want that. So we define 0 factorial to be equal to 1. Those are factorials. And this is NCR. Let's just show an example, 7 factorial. That's actually generally on a lot of calculators too. If they have NCR, they have factorials. 7 times 6 times 5 times 4 times 3 times 2 times 1. Pull out a calculator and show you both ways, just multiplying it out slowly. 7 times 6 times 5 times 4 times 3 times 2 times 1 is 5,040. On my calculator, yours might be on somewhere different on yours. Right there, I have above my x to the -1 button, it says x exclamation point. That's what I'm going to use. I can do, to get the same thing, I can do 7 shift to get to the button above. Hit that button. Notice it shows 7 factorial. I hit equals, and it gives me 5,040. Okay. I also have on my calculator NCR. And we'll use that in a second. So, how does this work? Let's go back to our x2. Let's do x to the 5th, or n equals 5. Whoa. Don't start that. There we go. So when n equals 5, we had x to the 5th plus we had 5x to the 4th, y to the 1st, plus 10x to the 3rd, y squared, plus 10x squared, y cubed, plus 5xy to the 4th, plus 1y to the 5th. And I had n over r. This is what the formula was. So in this problem, n equals 5. And r, is that our term number? I don't know. Let's figure out what r's got to equal. I can't do r equals 0. If I plug in 0, well, I could. Hold on a second. This is the first term, right? This is our second term. This is our third term, fourth term, fifth term, sixth term. So if I want, first term, this is actually, we want to use k equals, or we want to have 0 in there. This is like, how do I want to say this? Let me jump. Let's not jump to that formula right there. I want to illustrate how this ends up working here for each of these things. So for our first term, we got 1x to the 5th, y to the 0. N is 5. That's n is 5 consistently across the board. What I'm going to do is I'm going to do 5 factorial over 5 factorial 0 factorial. And these two cancel out because they're the same, and I'm just left with 1 over 1 is 1. The second term, I've got 5x to the 4th, y to the 1st power. This is 5 factorial over, there's a pattern here, 4 factorial, 1 factorial. And the top is 5 times 4 factorial. If I split that up, because 5 factorial is 5 times 4 times 3 times 2 times 1. But I could write this as 5 times 4 factorial. And I've got 4 factorial on bottom, 1 factorial on bottom. The 4 factorials cancel out, and 1 factorial is just 1. I'm left with 5. The third one was 10x cubed y squared. If I put the total number of the exponents on top and each of the exponents on bottom, how does this clean up? 5 factorial I can do is 5 times 4 times 3 factorial, just like I did up here. Or I could write it all out, but this is more convenient. 3 factorial over 2 factorial. I'm going to put 2 times 1 here, because at this point, it doesn't cancel out very well. 3 factorials go away. I've got 5 times 4 over is 20 over 2 is 10. Are you seeing what's going on here? These are the coefficients. Fourth one just switches this around. It starts repeating after you get to the midpoint. 5 factorial over 2 factorial, 3 factorial. Same process gets us a 10. If we put n on top, n factorial on top, and each of the exponents factorials on bottom, multiplied together, we get the coefficient. So I said, let's try something hard. Let's do like x plus y to the 13th power. Let's take a look at that. I don't want to write the whole tree, but I can do that. I know that there's an x cubed there, or x to the 13th there, a y to the 13th there. What happens, and notice when we started this off, the coefficient of the second term is always the exponent of the big binomial. So x plus y to the 5th power, 5. This one should be 13x to the 12th y to the 1st. And then I don't know the next one. Let's figure it out. So if I want to do this one right here, what's my coefficient got to be for x to the 11th, y to the 2nd? I've got 13 factorial over 11 factorial, 2 factorial, which is 13 times 12 times 11 factorial over 11 factorial times 2 times 1. 11 factorials cancel. 12 divided by 2 is 6. And 13 times 6 is 6 times 3 is 18, 78. So that should be a 78. And if I want to find out the x to the 10th term, y to the 3rd, I don't think I gave myself enough room to write that coefficient now. 13 factorial over 10 factorial, 3 factorial. 13 times 12 times 11 times 10 factorial over 10 factorial, 3 factorial. Those cancel. This is 3 times 2 times 1, which is 6. 12 divided by 6 is 2. So I've got 13 times 2 times 11. 143 doubled is 286, I think. Choose 3, 286. So that's how it works. Now my calculator, I have to enter the 13 before I hit NCR, and then I hit the 3. But you can do them by hand. That's why I was working them out by hand to show you. If we do the next term, just take a look at it. Why don't you pause the video and figure out what this is? Nine factorials cancel. 4 times 3 is 12. Those cancel with that 12. 10 divided by 2 is 5. 13 times 11 times 5 is 143 times 5. Let's see, 143 times 5, 500, and then 40 times 5 would be 200, so 715, I think. I'm doing that in my head. Let's see if I got it right. Or if I use the NCR button, 13, choose 4. Yeah. So that we would have a 715 x to the 9th y to the 4th. And it would keep going on downward. I think you get the picture there. So the coefficients, so x plus y to the n, they follow the pattern. We start off with x to the 5 or x to the n, y to the 0. We have an x to the n, y to the 0. And at the end, we have an x to the 0, y to the end. And as we go this way, x decreases by a power, y increases by a power. The coefficients come from either Pascal's triangle or the binomial theorem or binomial calculator or binomial coefficients formula. Where n goes on top. And if we say this is x to the a, y to the b, where a plus b equals n, the coefficient I'll put in front c equals n factorial over a factorial b factorial, like that. And that's in a calculator. This is a choose b. I'm sorry, n choose a. My bad. N choose a. Okay. And if I want to make it match up with the n choose r, what do I got to do? So if I want to say n choose r, then I've got n factorial over r factorial n minus r factorial. And now we have, this is x to the r, y to the n minus r. So could we write out a formula for the general term? So we could say that the binomial formula, we have n over r, or n choose r. That's another way of writing it. We start off with x is high. Like that. What happens if I do r equals 1 now? Which term is this? So like r equals 1. That's not n, that's r right there. No, that's backwards. I wrote that backwards. It's x to the n minus r and y to the r. And so let's take a look at r equals 1. What's going on? I've got x to the n minus 1, y to the 1. This is, if we look at up here, this is actually like our second term. Second term. So really, if we want to write a formula, we want to start at the first term. I could either say it's like this. For the r minus 1 term, we have what I just said right there. N choose r, x to the n minus r, y to the r. And if we wanted to write it as the kth term, r minus 1 term sounds funny. Let's look at kth term. So how kth term? Let's let k equal r minus 1. So how do I gotta change this formula to switch it to k's? Add 1 to both sides. I get r equals k plus 1. This looks funny here. Hold on, give me a second. I think let's just leave it like that. Kth term is silly. The easiest way is just write down your write down variables with increasing for y and decreasing for x exponents. That's step A. Step B, calculate coefficient with either the triangle if it's short, or doing n factorial over r factorial n minus r factorial. where these are the two exponents. Of the term. Okay. They like to be pains in the butt. The book's going to give you some problems that are a little bit more wonky. So let's look at some wonky problems. Let's expand out. Let's do x minus 1/2 y to the 5th power. And if I want to write this as x plus y, I could do x plus negative 1/2 y to the 5th power. My first term is definitely, we know the coefficients of this line, right? We did 5. We had 1, 5, 10, 10, 5, 1. Those were the coefficients. I think Pascal's triangle is pretty quick there rather than doing NCR for each of these. And so we have x to the 5th, y negative 1/2 y to the 0, plus 5x to the 4th, negative 1/2 y to the 1st, plus 10x cubed, negative 1/2 y squared, plus 10x squared, negative 1/2 y cubed, plus 5x, negative 1/2 y to the 4th, plus y to the 5th. So I don't want to necessarily use y, I want to use what's right here. This is effectively like a plus b to the 5th power, and now I'm doing a's and b's along here. Well, what's this one? We got x to the 5th, that just cleans up. This one's fine. To the 1st power doesn't change anything, we just multiply it, minus 5/2 x to the 4th y. And then negative 1/2 squared is 1/4. So 10/4 x cubed y squared plus negative 1/2 cubed. We're multiplying, we just multiply that out, it's negative 1/8. So minus 10/8 x squared y cubed. And 1/2 to the 4th power is 16. And the negative is an odd power or even power, it's positive. Plus 5/16 x y to the 4th plus y to the 5th. And the only way I would simplify that up anymore is I would simplify or reduce the 10/4 and the 10/8. Oh, shit. That is not, this is negative 1/2 y squared. So is that. Which changes that. That becomes negative 1/32. I failed right there. My bad. That was bad, David, bad. And they might give you something ugly like this. Let's keep the exponents small. Let's do 2 over m minus 3 root m. Go up to the 4th power. We're going to assume m is greater than 0. That way the fraction is good and the radical is good. So to the 4th power on Pascal's triangle, we have 1, 3, 6, 3, 1. This is a plus b to the 4th. And a equals 2 over m. B equals negative 3 root m. So I'm going to have a to the 4th power and I'll just write that out real quick. A to the 4th power plus 3a cubed b to the 1st plus 6a squared b squared plus 3ab cubed plus b to the 4th. Now let's plug in our a's and our b's. I've got 2 to the m over to the 4th power plus 3 times 2 to the m cubed times 3 root m plus 6 2 to the m squared, 2 over m squared, 3 root m squared plus 3 2 over m 3 root m cubed plus 3 root m to the 4th. Now 2 squared to the 4th power is 16. This is 16 over m to the 4th. And then I've got 2 cubed is 8. And 3 times 3 is 9. So 9 times 8 is 72. I've got square root of m on top, m on bottom, m cubed on bottom. Here I've got, it might be easier to write out what these are. We've got 6, 2 squared is 4, 3 squared is 9, and square root of m squared is m. On bottom I have m squared. Here I've got 3 times 2 times 3 cubed is 27. And then I've got cube root of m, or square root of m to the 3 halves. This is m to the 3 halves. Let's write this as m to the 1/2. That might be a little bit easier. And on bottom, we just have m. And here we've got 3 to the 4th power is 81. And square root of m to the 4th power is m squared. So notice m keeps going up by 1/2 of a fraction on top, going down by a thing on bottom. If I simplify this, this is m to the 5 halves on bottom. What's 24 times 9? This is 216. Oops, plus 216. Fuck, I'm going to make that positive. Let's make that positive. I did all that work with positive signs. Fail. I should have had negatives in there. We got m over m squared. That just leaves an m on bottom, right? And now I've got 3 times 2 times 27. I keep writing equal sign plus 162. M on 3½ on top, m to the first on bottom. We subtract exponents. I got m to the 1/2 plus 81 m squared. So you gotta, when you have these things, you gotta plug them in and be careful with that negative sign. I screwed up the negative sign here. I even screwed it up a little bit here, up here with the last one, but that's how these work. The overall, the formulas and what to do is easy to remember. The hard part is actually working this out and cleaning it up when you have shitty things inside. All right, that actually wraps up 11.4, and that's the last thing we're doing this semester. Peace. Bye-bye.